Okay, guys, can you guys hear me? Hey, guys, can you guys hear me?
Yeah.
Okay, perfect. Let's give it one more minute while we're receiving more attendance. Okay, one more minute. Because we always have some connection issues for the first lecture. A lot of new students, they're trying to log into the system, especially for the first lecture. All right, just give it one more minute before we get started. So like I mentioned in the group chat, for the first lecture, I always suggest the student can give it maybe 10 to 15 minutes in advance. So if you have any connection issues, you can always chat with me, figure out how to log into the system. All right. The same thing applies for our everyday life, right? You can't really wait for the last minute. Okay, just give me one more minute. Okay, some students still have some login issues. All right, it's 8:31, so let's get started. So, hello guys, welcome to my North American Math Competition lecture. Today, we're going to go to a new session, the counting and probabilities. So before we get started, because we have some new students joining our lecture, I would like to spend roughly 3 to 5 minutes, give you guys a little bit information regarding our lecture. So basically how the organization of our lecture looks like, different kinds of informations you need to pay attention to before we get started. Roughly 3 to 5 minutes, just as a quick start. All right. So the first one is, I think, as pretty much all the teachers likes to say, is the interaction. These days, due to the COVID-19 situation, pretty much everyone is doing their lectures on an online basis. So I believe this interaction is always important, regardless you do a face-to-face lecture or you do this virtual online Zoom lecture. So basically, in my lecture, it's pretty casual. As long as you have any questions, you can always bring it up. There are two ways for you to communicate with me. Well, the first way, which I most suggest, is basically using the audio. So I hope you guys already have a mic. So during the entire course of my lecture, any question, just let me know. Okay, so by default, as long as you enter the classroom, I will make you as a mute. Just try to minimize the interaction for our lecturer and for the other students. But you can always unmute yourself. So anytime, any question, unmute yourself, bring it up to me. This is the first way. Well, the second way is you can actually chat with me. So if you're not so familiar with Zoom, basically you're in your control console, you're going to see a bunch of options like mute, start a video, security. So all the way to the end, you're going to see three dots, more, right? You click that three dots. In the drop-down menu, the first option is chat. So basically you click the chat, you'll be able to go to the chat board. There are two ways for you to There are basically two ways for you to chat with me. One is you can just basically chat. So the receptance you can see is everyone. So your questions or your answers can be seen by every student. Or if you prefer, you can actually change from everyone to myself. So this will be considered as a private chat, right? So if you feel a little bit shy, you don't want your answers or questions to be seen by the other students, you can always go for the second option. That being said, as only me and you, we can see our communication. All right. But generally speaking, I think there's no judge. As long as you have any question, just let us know so everyone can see your question and see your answer. So there's not a big deal whatsoever. All right. Interaction, always important. Second, I want to talk about the homework. I believe the homework is a very important part in any kind of courses, not only for math, but also for pretty much everything. So, in order to have a better extension and better implementation of all the technology we introduced in the lecture, we like to give you 3 to 4 problems in a weekly basis. So our lecture is going to focus on the technology. It's the fish and fishing. Which one is more important? Of course, it's the fishing, right? So in our lecture, we're going to give you guys a bunch of technologies, how to solve different kinds of counting and probability problems. And of course, I'm going to give you some sample problems in order to use the technology. But our lecture is our limit, right? We have some limit for our lecture. Our volume is limited. So therefore, I need to give you more time after your lecture, try to reinforce the technologies. So that's the homework. So normally how it works is that after each lecture, I'm going to give you 3 to 4 probably like different problems, and you have 1 week to finish the problem. I'm going to mark your problem and give you the feedback. In the next lecture, I'm going to invite some students to give us a quick walkthrough for your problem. So bear with me. Generally speaking, I will basically ask one student to take one problem. And trust me, as long as I ask you to do a walkthrough or presentation, it means you do a good job. So therefore, there's no panic, right? I'm not going to make you as a fool, right? So try to be more confident. As long as I invite you, means you have the good answer. So try to be more confident. All right? And the last one is the presentation. So how presentation works. So basically every single lecture except for the first lecture, I'm gonna ask one student to give us a short and brief presentation. You can pick up any question you like. It can be a math competition problem or can be any interesting problem that you think should be suitable for presentation. The problem does not have to be super difficult or very flowery, so on and so forth. The most important thing I want to ask is that try to pick up a problem which is quite aligned with our topics. You see, these days we're talking about the counting and probabilities. So that being said, any kind of counting and probability problem you pick up from any kind of sources will work. Well, the most important thing is that I want to not only what should I say, be capable solving out a problem. But most important thing is that you need to think aloud. These days in any kind of top tier, if you go to the FANG, FANG, the top tier computer companies, like internet companies, the most important thing is you're gonna write a code on the whiteboard. So not only you can just basically give it a correct answer, but the most important thing, you can walk through the interview, like the interview process. So that's also, we like to take this opportunity to give you guys more chances, right? Have the correct answer and also try to present it in a very, very professional way. But we know that Rome wasn't built in a day. It took 100 years. So the same thing, gradually by gradually, hopefully we take all the opportunities to exercise and to train this capability. All right, I think this is like a short and brief introduction for the organization of our lecture. So you have any questions? Oh, good. All right. So before we get started into today's lecture, I'd like to give you guys a quick overview about what we're going to happen for the next 10 lectures. So in this 10 lectures, we're going to focus on the very interesting topic, counting and probability. Counting and probability is one of the 4 major sections in the North American math competition. We're talking about the 4 major sections: algebra, geometry, counting and probability, and number theory. Actually, if you want to do a comparison between these 4 sections, you're going to find out the counting and probability is actually something very different. Because either in algebra, geometry, or the number theory, you're looking at numerous formulas, theorems, right? It's way too much. However, in the counting and probability, you're not looking at so many formulas. Pretty much some permutation, combination, and some binomial theorem, and that's it. No more than 10 formulas. However, you're going to see like thousands of questions basically using the 3 formulas. So that being said, the counting and probability is actually a very dynamic process, right? A very dynamic concepts. You're going to use a very short, very small amount of like, what should I say, like the formulas, try to solve as many problems as possible. So this is a little bit different with the other sections of our North American math competition. In our lecture, we're going to spend our lecture, especially like the first 3 lectures, talking about the basic concepts of the counting and probability. So these basic concepts seems to be I think should be very familiar to you guys. However, I want to give you guys a little bit elaboration, how to use the basic concepts and how to understand the difference between like the basic concepts and try to use them to solve some relatively complicated problem. This is our focus at the first 3 lectures. And then moving forward, I'm going to go to a very important section is 25 types of counting problems. So like I said, there are numerous counting and probability problems based on relatively small amount of formulas. However, we need to make some classification. We need to make some conclusion, right? How to basically treat all those problems. Of course, we can't blindly go to each problem, give you a different technology. I have already classified all those problems into majorly 25 major types. So that being said, 99% of the problem will fall into 1 or 2 types of my 25 different types. So let's take this opportunity to go through this 25 types. Hopefully after this like a go through section, you'll be able to find out, okay, for any new problem, I'm going to classify into one of these 25 types, at least to give you guys a big direction how to solve the problem. So that's the second part. The third part, we're going to go to some AMC and AMY problem. So, each problem, what should I say? Each math competition, they have their order, right? People have a momentum. We always believe what we believe. So if you do a comparison between our Waterloo, our Canadian exams, and also our American exams, you're going to find out, yes, sometimes there are some problems always tested in the AMC, while there are some problems always tested in the Waterloo. So that being said, means the order of those 2 math competitions, they have their own momentum. So we're going to spend some time talking about some classical problems for the AMY and AMC. Try to give you guys some idea if you see some similar problems in the future in AMY or AMC, what are you going to do? And the same thing applies. We're also going to give you a section talking about the Waterloo problems. There are some problems that has been tested so many times in the Waterloo exam, well, never tested in the AMC. So we need to understand the drill. I'm going to give you some conclusion and try to give you some preparation for those exams. And moving forward, I'm going to teach you some advanced technologies in counting and probability. We're talking about some basic technologies in the first several lectures. Well, there are some difficult problems. So we're talking about some advanced technologies, something like the coloring method, like Giffibini method, the continuous adjustment method. So this method might not be necessarily used in every single problem, but the focus of our math competition is we want to really help to expand our horizon. Right? So after seeing some high-techy technologies in the future, if you see some relatively difficult problems, you won't be panic. At least you have some big direction to find out what is the possible approaches. All right. And then moving forward, we're going to talking about the binomial theorem. Right? The binomial theorem is actually a very important part, especially in the AMC exams. How to do the binomial expansion, how to determine specific coefficient in the expansion. That's actually a favorite part for the AMC, and that should be tested in the pretty much like in a yearly basis. And last but not least is probability. Now, the probability is actually an extension of the counting skills. So I'll say they are 95% similar. As long as you are a master of the counting skills, you should have no problem taking care of the probability problems. So that's the reason we put a probability at the end of the lecture. Actually, there are 2 parts or 2 types of a probability problem we like to discuss in our lecture. One is the classical probability. The other one is the geometric probability. The classical probability, I think you guys already see that in your day school or like whatever. While the geometric probability is pretty much a favorite for the North American math competition. Instead of doing a hard calculation for the counting skills, for the probabilities, geometric probability is always trying to use an area or like a volume to determine the probability. If you guys are not familiar with, please try to remember this is one of the very important topic in our North American math competition. And we're going to spend some time help you guys understand what is the common strategies when we're looking at these problems. All right, so hopefully that's a short and brief introduction about what we're going to cover in the next 10 lectures. Any more questions? All good? Okay, perfect, because I'm always monitoring the chat board during our lecture. So if you have any questions, just bring it up in the chat board, and I will be able to answer your question in a real-time basis. All right, if all good, so let's go to our first lecture. We're going to focus on the basic concepts. Number one, today we're going to focus on the enumeration method and casework. Enumeration method and casework. So before we actually jump to the enumeration method and casework, let's talk about something like broadly. Generally speaking, when we talk about the mathematics, we're basically talking about three types of problems. Mathematics contains three types of problems. The first type is complex problem. However, you have an elegant and pattern solution. Sometimes you have a very complicated problem. However, you can have a very elegant and have a very patternized solution. I'll give you an example. Let's say sine x can be written as x minus x cubed, 3 factorial, x5, 5 factorial, x7, 7 factorial, all the way minus 1 to the power of n, 2n plus 1, factorial, x 2n plus 1. So this is actually the famous Taylor's expansion, or we can say Taylor series. Okay, if you're not familiar, not a big deal. I just want to give you guys a little bit idea. You see, this looks like a complicated problem, right? You're actually to use infinite many terms of polynomial, try to denote the value of the sinusoid. Well, the good part is even though it's complicated, you have a very nice, very patternized solution. So as long as you know the solution, you basically have no problem figure out every single term. So this is the wonderful, wonderful scenario for the entire mathematics, right? Well, sometimes you have some other scenarios. You have also a complex problem, but there's no pattern. There's no regulation. For instance, our famous pi value, right? Pi is actually an irrational number, and there's no way to calculate, how many value, like how many bits for the pi values, right? And same thing applies for the e, right? For the ln, right? So these kind of thing is actually very complicated. There's no pattern. So I don't think you're going to see them in any kind of math competition. Maybe you're going to see them like in American Got a Talent or like all kind of like a talent show. If you can recite like 1,000 bits after the decimal point of the pi value, so on and so forth. So this is like the second type of problems we're looking at in the mathematics. While in the third part, we're trying to see some also complex problem. There are some pattern. However, this pattern is not elegant as the first one. For the first one, you can actually use one formula, one equation to solve the entire thing. Well, for the third part is they're a relatively difficult problem and they have like different patterns. So sometimes you cannot use only one pattern to summarize everything. In order to summarize everything, you have to break them into maybe pattern 1, and then pattern 2, all the way to pattern n. Okay? There might be n different patterns. You break them into n different patterns, and taking from there, you want to find out the representatives. Okay, what kind of representatives are good for pattern 1? What kind of things for pattern 2? What kind of representatives good for pattern 3? So on and so forth, right? So this is actually most of the problem we're looking at in the math. And why I'm saying this, and this is actually the basic concepts of the enumeration method. Okay, enumeration. So what is a enumeration? If you do some Google search, you're going to find out enumeration means list them out. List them out. That's the meaning of this word. However, there are two ways to list them out. One is actually what we're very famous is the exhaustion method. Exhaustive method. Exhaustive method means what? You list them out one by one. If you have 100 items, okay, you place them 1, 2, 3, all the way to 100. If you have 1,000, 1, 2, 3, all the way to 1,000. So there's no trick for exhaustive method, just from 1 all the way to n. It's very crappy. You have to list out everything one by one. However, enumeration method is a little bit smarter compared with the exhaustive method. You're also trying to list out them one by one. However, you are trying to do some casework. Okay? In the enumeration method, like I said from here, there might be some patterns. Your $1,000,000 question is try to find out what is the pattern number 1 and list out all the representative basically under the pattern number 1. And then what is pattern number 2? All the way, what is pattern number n? So the enumeration method actually has a very important technology is casework. So student might ask, hey, Alex, how can I make the casework, right? The casework might be, you might have one case, you might have 100 cases. And even for the same problem, maybe from time to time, you can basically do different kinds of casework. You can do, I just gave an example, I have a lot of human beings, okay? I have a lot of human beings in the room. You can actually do the casework, people, human. You can do the casework using their gender. In that case, you only have like 2, right? Okay, technically, this is not correct. If you go to the Facebook registration, I think they have like 32 different genders. But for our case, let's try to make our life easier, right? We're trying to be politically correct. We have 32 different genders, but in our base problem, you have only 2 genders, okay? Or you can go for different age. If you go for different age, at least you might have like 80 to like 100 different cases, right? And you can always go for different birthday. If you want to go for a different birthday, oh my God, you're gonna have like almost like 365 different cases. So that being said, the $1,000,000 question for us to do is that how can I do the casework? We need to find the right case that do not have so many cases and make my life a little bit easier. But maybe sometimes I need to find a case that must have some kind of scenarios that allowed me to do some, back and forth, to do some flexionation in this implementation process. So the $1,000,000 question is, how can I do this casework? Actually, to do the casework, there's a very important technology. We call it the SMART classification. So, like I said, if you want to do this classification, if you want to do the casework, it's always important to find out how to break them into different cases. Well, all those cases, you want to go for 2 golden rules. One is no overlap. One is no oversight. What is that? Let's say you want to break like a bunch of people into different groups. This is considered to be a case, right? You want to make sure for those 2 groups, any different groups, there's no shared people, right? If you have to share the people, your life can be very complicated. The same people, like the same person will be counted twice in group 1, in group 2. And then later you have to count, each one has been counted more than one time and then do some subtraction. So if you can try to make some classification to make sure there's no overlap between different groups. So your life can be a little bit straightforward. The other one is no oversight. Let's say you have already break all the people into different groups or different cases, then you want to make sure there's no leftovers, right? Your cases can cover every single people, and these people will not be left from any groups. So this is considered to be a no oversight. Okay, 1, 2, 3, 4. For instance, there's no leftovers. So for the entire lecture of the counting and probabilities, I'm always going to teach you how to find out your cases to make sure there's no overlap, there's no oversight. Trust me, it sounds easy, but might not be so doable whenever you use different and especially complicated problems. But no problem, let's do this one by one. Try to make sure, as long as we do the casework, I'm going to remind you, try to do a SMART classification. So what does the SMART classification mean? It means you want to make sure there's no overlap, there's no oversight. All right? So moving forward, I'm going to tell you guys some real problems using this enumeration technology. Trust me, in the North American competition, whenever you're using the casework, whenever you're using the enumeration, you're basically looking at two types of problems. These are the two major types of problem. One is the root-related problem. It means you're kind of like walking a matrix, or you have like you have a big grid, you want to go for a different route, right? This is kind of root-related problem. Well, the other one is the number or letter-related problem. Okay, so these two problems are quite similar, but also they have own technologies. So I'm gonna give you some examples from these two categories. So let's try to summarize some common technologies you're looking at for those problems. All right, so let's get started. Let's go to the first part, the route-related problem. Okay, let's go for our question number one. Question number one says something like this. As shown in the diagram, Peter starts from point A to point B. He can only move one step at a time, and he must move to the right or to the south. Please determine how many ways he can move from A to B. You're basically looking at a matrix. This is A, this is B. Okay, you have a matrix. This is a 4 times 5 matrix, and you basically have a point from A. So Peter wants to move from A to B. Every single time he can only move one step, and he can only move to the right and to the south. Means he must be able to do this way, but he cannot go back, right? Go back, this is not acceptable. Okay, with all those information, please try to determine how many steps or how many scenarios that Peter can move from A to B. This is a basic problem. I think it's very straightforward, but we want to take this straightforward problem to indicate a lot of important technologies for our counting and probabilities. Move up a little bit. Okay, no problem. There you go. All right. So a problem like this, how are we going to solve this? Okay. So before we get started, I think it's quite understandable. Like people, you can do that way, right? So there are so many ways for Peter just basically to move. He can do something like this. He can do something like this, or do something like this, or do something like this. There are like looks like so many ways for Peter to move. If you want to do the count, you better be smart, right? So this is actually where the smart classification and counting technology kicks in. Actually, think about it. In order to go from A all the way to B, so in order to go to B, Peter has to go to either, let's say this is 1 point, this is 2 point, right? From 1 point, he can go south in order to reach B. From 2 point, he can go right in order to go to B, right? So there's no way for Peter to go from this one to B, right? This is quite understandable because he can always go to the right, he can always go to the south. So that being said, maybe if I can figure out the number, how many ways that Peter can go from A to here, how many ways that Peter can go from A to 2, then adding those two scenarios together, I'll be able to get the total numbers that Peter will have to go from A all the way to B. Is that right? We're on the same page, I think. So this is actually easy, but it actually reveals a very important technology in accounting. In the counting territory, trust me, most of the time you are trying to do some reverse engineering. When you are looking at some complicated problems, always try to think about, can I start from the very last and reverse back? So this thinking process, because think about it, always from the very beginning, you have so many scenarios. All your things actually diverge. But all the way you go to the end, your scenario become limited. Is that right? So if you're starting from here, you might be able to see, okay, I just basically to add up those two scenarios together and you're good to go. All right. If that's the case, so as long as I know, okay, how many scenarios I can get into 1 and into 2, I'll be able to solve the problem. And I can do the same thing, right? As long as I figure out how many ways from here, and then I will calculate all those numbers to here. Okay, as long as I know how many ways I can get from here, I'll be able to determine how many ways I can get into 1, so on and so forth. So that being said, maybe we will be ready to calculate how many ways that Peter can walk from A to B one by one. Okay, so let's try to do it in this way. Let me just take it back. Let's say here. For Peter to go to this point, there's only one method, right? Because he just basically moved to the right. To go to this point, there's only one method, even though Peter has to go for 2 steps, but there's only one way for Peter to go to there. You're just basically moving to the right. And same thing, 1, same thing, 1, same thing, 1 here, right? This is quite understandable. And the same thing applies if Peter wants to go to this point. There's only one method. There's only one method, one method, one method, right? You can just basically go south. You can go for multiple steps, but there's only one method. There's no way around. But in order to go to this point, Peter actually has 2 methods. He can go from this way or go from this way. There are actually 2 methods. Is that right? So these 2 methods can actually be considered as the sum of those 2 numbers, right? Still remember our analysis? In order to go to our point here, we need to either go to our first point here and then go to the second point here. You just have to add the 2 scenarios together. That will give you the total number, the total scenarios that A will be able to go to the second point. Same thing applies here. 3, because you're adding these 2 adjacent diagonals together, right? And then this is going to be 4. This is going to be 5. Okay, so this is going to be 3. You're adding 3 and 3, that's going to be what is 6. 4 plus 6, 10. 15. 4, 10, 20, 35, right? There's no magic. You just basically do this counting those numbers together. 35, 70, 6, 21, and 56, and the answer is 126. So Andy has the correct answer already, but I like to walk through the process. So that being said, you will be able to count all those numbers one by one. So all the way B has a point 126, means there are 126 ways to go from A all the way to B. You see, there's no technologies here. You're just basically doing the counting, right? You list them one by one. So this is actually solution 1 for this problem. Okay, you have 120. Because you have a relatively small grid, it's 4 times 5. But what if I give you a big grid, 40 times 50? Can you also do the same thing? Of course you can, but that's going to take enormous time, right? So every problem, we want to do a little bit extension, okay? So this guy, we know, okay, counting them, good enough. But what if I have a huge grid? Do we have something more analytical in order to solve the problem? I think we do. So that's the extension problem 1-to-1, okay? Let's forget about like the real counting one by one. Let's try to use some analytical way how to solve this. So again, I'm gonna put it one more time. You have 1, 2, 3, 4, 4 rows. 1, 2, 3, 4, 5, right? From A all the way to B. Let's try to think about it. At the very beginning, Peter stands at here. At the end of the day, Peter stands at here. So that being said, in order to get from A to B, Peter must move downward 4 steps, right? And rightward 5 steps. Is it right? I don't really care the order, but at the end of the day, Peter wants to go from A to B. He must go down 4 steps. He must go to the right 5 steps in order to go to the B point. Okay, so let's just try to list up. Let's say the 4 steps going downward. I'm gonna put a name, maybe going down, 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 down for these. And 5 steps going to the right. 1, 2, 3, 4, 5, right? So that being said, at the end of the day, if you want to tell me a pattern or like a routine that Peter takes from A to B, it will be nothing but something like this. D, 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 R, 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 R. This is one scenario. Or maybe D, R, D, R, D, R, I don't know, maybe D, R, R. Something like that, right? You can actually write as many as you could. Okay, so that being said means what? Means that if I just want to make some permutation for all those numbers, D, 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 R, R, 4 Ds, 5 Rs, I will be ready to figure. If I know how many permutations for these 4 Ds and 5 Rs altogether, then you will be able to determine how many steps in total. Is that right? But this permutation is not exactly the same permutation we regularly talking about, right? We regularly talking about is like the unique number permutation. Let's say if I have the D1, D2, D3, D4, 4 different Ds, R1, R2, R3, R4, R5, 5 different Rs. Okay, there's 9 elements. I want you guys to do a permutation, a full permutation. I think everyone knows that. That's going to be 9 factorial. Is that right? 9 factorial. Different Ds, different Rs. Put them together, full permutation, 9 factorial. However, don't forget, those Ds are actually the same. Is that right? So let's say in this one, D1, D2, D3, D4, R1, R2 all the way to R5. And maybe you want to put D4, D3, D2, D1, R1, R2 all the way to R5. Okay, let's forget about this R part. These Ds are actually the same. Is that right? D1, D2, D3, D4 is the same as D4, D3, D2, D1. They're actually the same item. So that being said, means those D values, their order doesn't matter. Is that right? So if you're directly using 9 factorial, you are overcounting too much. Is that right? So what are you going to do? You have to eliminate your overcounting part. What is the overcounting part? Check it out from here. There are actually 4 Ds. Those 4 Ds, you do whatever permutation you like. For me, it's the same thing. It's exactly identical. There are 5 Rs. 5 Rs, you do whatever you like. For me, this is actually identical. So you are actually overcounting 2 parts, all the Ds and all the Rs. So what should I do? I just basically have to over 4 factorial times 9 factorial. 4 factorial means all the D's, you do your magic, you do different kind of full permutation. Unfortunately for me, it's the same thing. All the R's, you do all your magic, all your permutation. Unfortunately for me, it's the same thing. So therefore, I need to eliminate all of you guys, do a division. So that is actually the correct solution for this problem. 9 factorial over 4 factorial times 5 factorial. So that one gives me the same answer, 126. So far, so good? Any questions? So this is more like 2 ways, right? You can use a really counting way, or you can actually use our solution too, using an analytical way. All right. If all good, let's go for another extension. It's one problem, but we want to do as much extension as possible. Let's go to extension number 2. 1-2. Same thing. Exactly the same thing. Nothing has been changed. Right? A is here, B is here. Peter also want to walk from A to B. But today, there's a big rain. And after the big rain, you see a lot of mud pond. Okay? In the street. So the mud pond goes from here. Some mud pond. So whenever you have the mud pond, it means that some points are no longer accessible. So Peter will not go to the mud pond. Peter has to go outside the mud pond. If that's the case, my question for you guys is that how can we calculate the ways that Peter from A to B? Okay, some of the stuff is no longer accessible. Some of the points is no longer accessible. So can you tell me how to get from A to B? Who likes to give us some idea? Exactly the same thing? Exactly the same fashion? Always move to the left, always move to the right, always move to the south. But however, there are some points no longer accessible. Is there any trick I can do in order to make it easier? Trust me, every single extension, you're not gonna do a huge jump, just like a tiny, tiny jump. But try to understand the differences between all those problems are actually extremely important. So let me ask you another question. So having this mud pond, it means what? There are 6 points here, right? Previously, Peter has the capability to go to those 6 points. But for now, Peter can no longer go to those 6 points. Is that right? So that's like a human language. How can we convert this human language into something more mathematical? From a mathematical perspective, it means those 6 points will do what kind of changes? Think about it. For now, Peter can no longer go to those 6 points. That's a human language. But how can I convert it from the human language into a mathematical language? As long as you know this, you'll be fix the problem in about 30 seconds. Yeah, I see some students has the correct answer. That is perfect. It means that what? Peter can no longer go to those points. Means the chance or the scenarios go to those things actually goes to 0. Is that right? Go to 0. Previously, you can go there. You can have a 20-way, a 200-way, whatever you like. But for now, that thing goes to 0. Okay, if that's the case, means what? The other stuff never changed. Peter come to here, you still have one way, one, one, nothing changed. Here's also one, 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 one. Here's also 2, 3, 4, 5. But here, check it out from here, I'm changing a different color. Here it becomes to 0. You have no way to go there. 0, 0. So that being said, here will becomes actually 5. 0 plus 5, 5. Here is also 5, right? Here is 1, 1, 1, 6, and 2, 3, 4, 10. Okay, so that being said, by covering this 6 points in the middle, you have already reduced from 160 all the way to only 10 ways. The ways has been significantly reduced, right? From 160 to 10. The only reason is because everything that has been covered, let me change a different color, everything that has been covered by this mud pond is no longer accessible, right? As long as it is no longer accessible, so you don't have to waste your time. You can just basically put all the values into 0. So far, so good? Trust me, this is actually a very valuable extension. If you check the problem from AMC 12, this is 2010, AMC 12A, question number 18 is exactly the same thing. This is exactly the same thing as this. You can go back, check this problem. So try to use exactly the same technology and you'll be able to solve it out. Okay, a single problem as a quick start, and we extend it twice, and you'll be able to see all those kind of flowery properties from such a single problem. All right, so far, so good? Okay, if all good, let's go to another problem. Question number 2. Question number 2 is a problem that I choose from 2012 AMC10B, question number 25. It's a difficult problem from AMC10B. However, trust me, it used nothing but the enumeration, all the technologies we talk about. Okay, this is also a famous route-related problem. Okay, let's have a look. So the problem says you have a bug, travels from A to B. Have a grade, right? Same thing. Along the segment in the hexagon lattice of the picture below. The segments marked with an arrow can be traveled only in the direction of the arrow. So something like this. Here, the bug must travel in this direction. Here, it must travel in this direction. However, if there's no mark, you see, from here, here, these kind of things, it doesn't matter. The bug can travel up, down, or like downward or upward. It doesn't matter. There's no directional. It's not a big deal. And the bug never travel the same elements more than once. Okay, you always travel only once. So how many different passes are there getting from A all the way to B? Okay, how many different passes you can have getting from A all the way to B? All right, let's think about it. How are we going to do such a problem? For the AMC, as long as you see the problem, you see like your question, my suggestion is always check the A, B, C, D, E, the options first. If the number is only 3, 4, 5, don't waste your time. trying to list them out one by one, right? But now you see the numbers that are kind of innumerous, 2,000 something. Okay, it looks like there's no way for you to list them out one by one. You need to find some technologies, some tricks in order to figure it out. Okay, from A all the way to B. Let's have a quick look. I think this is really complicated. You see, from A to B, you can go from here. That's the most straightforward one. Or you might go, I don't know, do a quick return and then go here and then go here and then go here. And maybe go here and go here, right? There are so many ways. Plus, you see there are 2,000 ways. It is impossible for you to basically cover them out one by one. So that being said, you must do some casework. Like I said, right? The $1 million question for the casework is you classify them into different cases, and then you pick up a representative. As long as you know the representative, and then you know all the properties for the entire case. So you don't have to count one by one for the entire case, right? Okay. Well, the thing is, how can I do the casework? That's a $1 million question I'll be asking for the entire lecture. You see, like the bug can travel wherever it likes to travel, so it looks like so complicated. However, I find there are some points, there are some levels, if I say, as long as the bug traveled past that level, it will never be able to return back. Let me repeat it. A quick observation for this picture, I have a feeling that there are some levels. As long as the bug passes that level, there's no way for the bug to come back. And who can tell me what those levels are? This is extremely important. That's actually the breaking point for our casework. Who can tell me this? There are some levels. As long as you pass it, there's no way for you to come back. Yep, I see some students have some ideas. What about the other students? Okay, yes, that's correct. Let's check it out from here. Let's say, I'll give you one example. Let's say here, I call line number 1. If the bug pass line number 1, because you see all the arrows on the left-hand side of this line number 1 is actually pointing to the right. So that being said, as long as you're passing line number 1, there's no way to go back to A point. Is that correct? This is the first one. We need to think about it. Maybe it's a casework. Then what is the next one? Yeah, perfect. I see students have the answer right away. Yeah, this is actually line number 2. You see? As long as you pass line number 2, the same thing, because on the left-hand side of the line number 2, they're all arrows pointing to the right. So that being said, if you pass line number 2, there's actually no way for you to go back. And the same thing, line number 3. Line number 3, right? The same thing, as long as you pass line number 3, there's no way for you to go back. So that being said, maybe I need to do my casework based on these 3 lines. I'm gonna see, let's say, how many ways that the bug can go to here, can go to here. Because as long as I know this, I know moving forward, there's no way for the bug to return. How many ways the bug can come here, can come here, come here, come here, right? So let's give a name. 1, 2, 3, 4, 5, 6, 7, 8. Is that right? As long as I figure out how many ways my bug can go to that point, I will be able to decide moving forward, nothing will be changed backward. I'm going to move my work to the next step. So that being said, my casework might be able to break into 1, 2, 3, 3 different scenarios. Guys, follow me? This is very important. Well, I think the first one is very easy because there's only one way to get from A to this one. There's only one way to get A from this one. So I think this is too easy, so don't waste our time. I'm going to erase this. Let's just focus on some difficult part. Okay, for line number 2, how many ways? Let's go here. For line number 2, how many ways I can get from A to 1? From A to 2, A to 3, A to 4, right? This is my first case discussion. And then we're going to talk about our second case discussion. Is that right? Okay, let's dive into the first case. How many ways I can go from A all the way to A part? Okay, let's try to break it down into here, our casework. I'm gonna take the picture here one more time. Okay, here, I just need a picture here. So we're talking about here, right? This is line number 2. This is a 1, 2, 3, 4. I want to see how many points how many ways A can get, like the bug can get from A to 1. I think this way there's no magic. The only thing you can do is do the enumeration, list them out one by one. You can just do some route. Let's check it out. How many ways I can get from A all the way to the 1 point? Okay, so maybe I'll do because another quick thing I want to have a quick look. Due to the symmetric property, the ways that A get from 1, like the points, like the bus get from A to 1, is actually the same from A to 4, right? Because these 2 points are actually what? Symmetric. The same thing applies. The ways that the puck get from A to 2 is actually the same as the A to 3. Right? Because these 2 points are actually symmetric. So you don't have to you don't have to calculate twice. Calculate once is good enough. Okay? So as an example, I'm going to show you how many ways the bug can get from A to 4. Let's check. The first one, let me see how I can get. The first one is actually directly going down, right? Here to here, 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 here. This is number 1. And number 2, I go up a little bit. Here, 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 here. And then I will do the same thing as my first routine, right? All the way from here to here. This is the red color, number 3, number 2. And what else? What else? I might be able to do something like this. I'll change to green. I might go up here, go up, and then I go down. I come to here, and I go back. Come to here, and then I'm gonna merge with the previous 2 lines as well, right? Here all the way to here. This is number 3. What else? I can try go for number 4. Go this way. Go here. I use the brown color. Here. 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 Go down. Go here. Go here. Go here. Go here. Go here, right? This is number 4. What else? There's a last one. Let me change another color because for this problem, you really have to use different colors to make it happen. Okay, the last one is actually starting from A, go up, go here, go here, go here. Go here, 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 here. This is number 5. Trust me, there's no magic. You just have to list them out one by one. So that being said, okay, there's only 5 ways. I tried my best. I didn't find the other ones. Okay, you want to make sure you only cover them once and there's no go back, right? Every single segment only cover once. So that being said, from A all the way go to point number 4, you have 5 ways. Using this symmetric property, you also have 5 ways to get from A all the way to number 1 point. So far, so good? Okay, let's check out the second part. How can I get from A all the way to number 2 or number 3 point? I have to drag another picture because I'm going to draw another bunch of routines as well. Same thing, exactly the same thing. Nothing has been changed. Same technology, one more time. So we're talking about this guy, right? Here. So this part I have already figured out. Number 1, this is 5, right? Number 4, this is also 5, right? This is what I just calculated. So my goal is to calculate how many ways that the bug can get from A all the way to 2 and to 3. Let's just check it out one by one. The same thing. The first one to go from A to the number 2 point is I go here, 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 here. This is number 1. Okay. Number 2, I'll go downward here, 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 here. This is number 2, right? There's no trick. You really have to list them out one by one. And the third one, let me change the color. The third one will be a little bit nasty. You go from here, come to here, here, downwards, go to here, and then you're going to merge with the red one. This is number 3, right? And number 4 is you go downward first, come to here, 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 here. Number 4, right? And the last one is the most complicated one. You want to go here first, take a big turn, here, 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 here. Okay, you take back a little bit, and then go here, go here, go here, go here, go here. Take the biggest route. That's actually number 5 as well. So that being said, if you want to take from A all the way to the point number 2, you also have 5 different routines. Is that right? And using the symmetric property, A to 5, A to 2, and A to 3, there must be identical. So that being said, you must also have 5 ways to go to the 3 points. So far, so good? There's no magic. We just have to list them out one by one. Okay, if so far so good, that being said means what? I'm just going to redrag it one more time. That being said means to here. In order to go to our line number 2, from here to here, here, here. From A to 1 point, you have 5 ways. A to 2 point, 5 ways. A to 3 point, 5 ways. A to 4 point, 5 ways. Okay, we're finishing our case number 1. talking about the line number 2. Okay, so far so good. Now we're going to talk about line number 3. Line number 3. Line number 3 has another 4 points. Okay, this is number 5, number 6, number 7, number 9. Okay, so do you still remember what I mentioned previously? At this moment, because we're doing the casework, all the cases, there's no overlap, there's no oversight. Since I have already helped you taking care of case number 1 here, from A all the way to 1, 2, 3, 4, 4 points. So as long as you're talking about case number 2, line number 3, case number 2, line number 3, you don't have to start from A. Because like I said, all the cases, they're segregated. Is that right? So for now, what I have to do is that I have to figure out how many ways that I can work from 1 point to 5, to 6, to 7, to 8. How many ways I need to write from 2 point to 1, to 2, to 3, to 4. And 5 and 6, yes, for these two guys, it's actually symmetric. So you don't have to waste our time. So far, so good. So that being said, for the next part, I don't think I need to really draw the lines one more time. I'll leave it as a homework, but there's no magic. You just have to draw them one by one. Okay? Then you will understand, okay? You will understand that, let's say, in order to go to this number 5 point, in order to go to number 5 point, you can go from number 1 to number 5, right? You can go to number 2, number 5, number 3, number 5, number 4, number 5, okay? 1, 2, 3, 4. Those 4 points, they can all go to number 5. So you can really list out them one by one, and then you'll figure out there are 4 ways. There are 8 ways, 8 ways, 4 ways. There's no magic. If you check the AOPS, Richard just basically list them up one by one. Okay. So from here, we want to say something. In order to get from number 1 point, let me change a different color. Maybe it's easier for you to understand. From number 1 point, go to number 4 point, go to number 5 point. You have 4 ways. But the question never asks you how many ways you go from number 1 go to number 5. The question asks you how many ways you get from A to number 5, right? But that part you should understand, because we have already calculated from A to number 1, you have what? 5 ways. And from number 1 to number 5, you have 4 ways. So that being said, from A to number 5, you have 20 ways. 4 times 5, which give you 20. You guys follow me? So far, so good? Okay, perfect. Okay. So from number 2 to number 5, you have 8 different methods. But originally, the question says from number A to number 2, you have 5 ways, right? This is what we introduced to here. From A to 2, you have 5. So from 2 to 5, you have 8. So that being said, from A to 2 to 5, you have 40. Right? Same thing. A to 3, you have 5. 3 to 5, you have 8. So from A through 3, you go to 5, you have 40 as well. A to 4, you have 5. 4 to 5, you have 4. So from A through 4 to go to 5, you have 20. Okay? So that being said, if you add everything together, from A to go to number 5, you have what? 20 plus 40 plus 40 plus 20, you have 120 method. This is the way how you get from A to 5. You have 120 different methods. You guys follow me? I'm gonna draw the graph one more time. This is a very difficult problem. Even though it's AMC10, even though it does not use any flowery technologies, but it really has to involve a lot of enumeration, a lot of casework. So don't forget, at the very beginning, we talk about here, 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 5, 5, 5, 5. Now we're talking about here. This is number 5, number 6, number 7, number 8. So now I already come to conclusion from A all the way to number 5, I have 120 scenarios. Using the symmetric property, the A to 5 will be exactly the same thing as A to 8. So that being said, you also have 120 scenarios. And these two guys in the middle, trust me, you will do the same thing, the same calculation. You figure out how to get the number from number 1 to number 2, number 2 to from number 1 to number 6, from number 2 to number 6, number 3, number 6, number 4, number 6. And then don't forget to count how many ways from here, which is 5, then you will count out. This is 120 as well. Okay? So far, so good? Are you guys following me? Can I have some feedback? Yes or no? Can I have some feedback? Yeah, this is a little bit time consuming, but I don't think it's difficult to understand, right? This is quite you just count. I'm not actually using any technology, just basically count. Okay, we're not done yet. We're just finished number 3 line. And then we have to finish all the way to the B part. So last diagram. Oops. Scroll it down a little bit. Sometimes a little bit laggy. Okay. Let me drag it down from here. And we're good to go. Now we are already done with here, right? We are already done with here. I know this is 120, 120, 120, 120. I still have to go to here. My work is done whenever I go to the B point. So that being said, I need to count. This is number 5, number 6, number 7, number 8. What I need to count is that from number 5, I go to the B point. How many ways I can go? Again, since I'm already done for this part, you see? This is our first case. This is our second case. We now go to our case number 3. From here, how many ways I can get from this number 5 all the way go to the B point? Unfortunately, there's no flowery things. List them out one by one. You will find out actually 5. This is pretty much just list them out. And using the symmetric property from number 8, go to the B. You also have 5, right? Also have 5. And from number 6, go to B. You have to list them out one by one, following all the curves. You'll find out it's also 5. And number 7 to P, also 5. Okay, I'm going to do exactly the same thing. Because I know from A to 5, I already calculate out there are 120 ways. Plus, maybe I shouldn't use plus. I just use this, okay? And from 5 to B, you have 5. So therefore, from A through 5, go to B, I have 600. 5 times 120. Same thing applies. A, go to number 4. A, go to number 6, excuse me. A, go to number 6 is 120, which is calculated here. 120. And 6 to B is 5. So in total, from A through 6 to go to B, you have 600. Same thing. A go to 7, 120. 7 go to B, 5. A through number 7 go to B, 600. A go to number 8, 120. A go to number A through number 8 go to B, 600 as well. So in total, from A all the way go to B through 5, 4, 6, 7, 8 will be 600 plus 600 plus actually equals to 2,400, like 2,400 ways. 2,400 ways. So the correct answer for this problem, this is a very time-consuming problem, I gotta say, is actually E part, 2,400. Okay, just a quick recap for this problem. Never be, what should I say, be confused with the complexity of the problem. Okay, our lecture is not here to confuse you. Well, on the contrary, what I'm trying to teach you guys is how to do the casework, right? Let's try to do some abstraction, abstract out the most important part of the problem. So for this problem, $1 million question for you guys to should know is that how to break them into 3 different parts or 3 different cases. And these 3 cases must be no overlap, excuse me, and no oversight. Is that right? So how can we do the breakdown? I think the $1 million question is we need to find a point as long as, or like a line, whatever, as long as the buck passes through that line, there's no way for the buck to go back. Is that right? So we find out, let's do a cut from here. This is our face number 1. As long as you pass line number 2, you can no longer come back. This is our face number 2, right? Something in the middle, this is our number 2. And this is our case number 3. Okay, these are actually the 3 cases. In order to make sure the bug cannot go back after passing a certain point, these are the 3 different regions. So when you're doing the calculation, try to focus on the 3 regions. Okay? So far, so good? I think this is what we want to say for this problem. This problem is a little bit difficult, but I don't think it's complicated. What should I say? It is a little bit complicated, but I don't think it's too difficult because they're not using any flowery technologies. You just basically list them out one by one. However, it has so many caseworks. You really have to understand one after another for all the casework. Okay? So far, so good? This is pretty much what I want to say regarding all the route-related problem. Okay? Taking the routes, taking all the grid, so on and so forth. These are pretty much the most complicated. You won't be seeing anything more than this. Okay? So if all good, let's go to another very important topic, the number or the letter related problem. Let's check it out. Number or letter related problems. Let's go for another problem. Problem goes like this. 4-digit integer can be written as ABCD. Okay, just give it a denotation. And the value of each digit is chosen from 1, 2, 3, 4, 5. Values can be repeatable. If the difference of any two adjacent digits is 1, then this 4-digit number is called close integer. Such as, I'll give an example, 1, 2, 3, 4, or 2, 3, 4, 5. 2, 3, 4, 2, 2, 3 as well, right? So determine how many close integer you can find in this question. I'll let you guys finish the writing first. You have a 4-digit integer can be written as ABCD. Just do a like a bar or something. And the value of each digit is chosen from 1, 2, 3, 4, 5. But it can be repeatable. You can choose 3 twice, 2 twice, whatever times. It's not a big deal. If the difference of any two adjacent digit is 1, then this 4-digit number is called a close integer. It's kind of definition, right? You see, they always ask you something like this. If you're familiar with Euclid, like it's always something like, we define a specific thing. I give you an example, 1, 2, 3, 4, or 2, 3, 4, 3. So to answer Andy's question, yeah, they're not necessarily increasing. They can be go up, go down, right? Not necessarily increasing or decreasing. Okay, with all those information, please try to tell me how many close integers can be defined in such a problem. Again, how do you think whenever you see such a problem? Okay, the $1 million question we're going to talk about for the entire lecture is how do you think, right? Apparently, I put it here. We're going to do the casework for sure. That's why I put it here, right? How do you do the casework? Like a $1 million question you might ask for yourself is, if I want to do the casework, how can I do the casework? I must do what? The SMART classification, right? Change the color to red. SMART classification to make sure there's no overlap, there's no oversight. Okay, how can I do this classification? That's a $1 million question, right? So trust me, I'm gonna give you some trick. Any kind of this letter-related problem, letter or number or like whatever related problem, the most effective way to do the casework is to focus on the digits. Focus on the bits, the 1's bit, 2's digit, 10's digits, like the 1's digits, 10's digit, 100's digits, like 1,000 digits, something like that. As long as you focus on the digit, focus on the bit, you will be able to do your casework in the most efficient way. Let's check it out, how I do this work. Let's say at the end of the day, I'm going to have like a bunch of numbers, 1, 2, 3, 4, 4, 2, 3, 1, so on and so forth. But if everything is is kind of like tangled together, there's no way for me to get started. In order to start my work, I must have to move one step out. I need to do 1, 2, 3, 4. I need to know what is the, let's say, the first digit. And taking from there, I will be able to figure out what is the second digit, what is the third, what is the fourth. Is that right? In Chinese, we have a saying, 千里之行，始于足下. Like the same thing applies for our mathematics. You're gonna like a baby step, right? You have to basically have a baby step first. So let's talk about it. 1, 2, 3, 4. Let's just focus on the highest digit. If you want to do the lowest, it's not a big deal. We'll just pick up one. For the highest digit, how many ways I can put? I can put 1, 2, 3, 4, 5, right? As long as I put one of them moving forward, I'll be able to determine the second, the third, the fourth, so on and so forth. So that being said means my casework can be done focusing on the highest bit. So this is actually my casework. Okay, case number 1. The first bit is 1. As long as the first bit is 1, the second bit can only be 2, right? Difference is 1. As long as the second bit is 2, the third bit can either be 1 or be 3. That's it. As long as the third is 1, the last one can only be 2. As long as the third bit is 3, the last one can be either 2 or 4. That's it. So therefore, if I start with number 1 as the highest bit, as the highest digit, there are only 3 scenarios. See? Easy peasy, right? Okay. Then I go to case number 2. If I start with number 2, the second digit can be 1 or can be 3, right? If I have number 1 as the second, the third one can only be 2. If I have number 3 as the second, the third one can be 4 or can be 2. Very intuitive, right? If I have this number 2 as my third digit, my last digit can be 3 or can be 1. If this guy is going to be 5 or 3, right? This is going to be 3, this is going to be 1. So in total, I have how many? 1, 2, 3, 4, 5, 6. I have 6 different digits. See? This is not a magic, right? It's so understandable. Okay, then practice time for you guys. Who can tell me if I start with number 3, how many numbers I have in total? Everyone, it's time for your participation. Please let me know if I start from number 3, then how many numbers I will have in total. Yeah, I see many students have the correct answer already. Yes. Let's give it another couple of seconds. Please, everyone, please participate in the process. This is not a magic, right? You can just basically list them out. Okay, perfect. I see pretty much everyone has the correct answer. It's 6. Numéro 6. Okay, so how to do that? Just one more time. It's easy. 3, the next one must be 2 or 4, right? If it says 2, the next one can be 1, can be 3. If it's 4, the next one can be 3, can be 5. If 1, the last one can only be 2. If 3, the last one can be 1, can be 2 or can be 4. This is can be 2, can be 4. This is only 4. So in total, you have 6. Right? Okay. If that's the work, case number 4, case number 5, who can tell me this? Maybe let's focus on number 4. If I start with number 4, who can tell me how many cases? Yeah, 6, right? 4 will be what? 4 will be 5 or 3. 3 can be 4, can be 4. Oh, 5 can only be 4. 3 can be 2, can be 4. 4 can be 3, can be 5. 2 can be 1, can be 3. This can be 3, this can be 5. So in total, 6. And what about 5? How many cases if I start with 5? 3, right? How many cases you can start with 5? 3. 5, the other one can be 4, can be 3, can be 5, right? 3 can be either 2, either 4. 5 can only be 5, can only be 4. So in total, 3. So your goal is try to add all the cases together, right? So starting with 1, you have 3 cases. Starting 2, you have 6 cases. Starting 3, you have 6. Starting 4, you have 6. Starting 5, you have 3. So altogether, you have 24 cases in total, right? You have 24 cases in total. Actually, this is the very beginning of our lecture. If with the moving forward, like what should I say, among like the moving forward, among the, like moving forward of our lecture, you don't really have to calculate that much. You can find out actually, starting with number 1 and starting with number 4, with number 5, they're actually symmetric. Is that right? So they must have the same number of cases. Same thing, number 2 and number 4, they're actually symmetric as well. So they must have the same number of cases as well. Think about our previous problem, our like this nasty bug problem. Every time I use a lot of symmetric property. Trust me, in counting on probabilities, using this symmetric property can actually significantly reduce your calculation time. So I'm going to give you more exercise and more examples in the future, and you will be able to get a hang of it. All right? Try to do more symmetric. Do not do too much hard calculation. Symmetric property can significantly help you do this. All good? All good. Let's go for another problem. We have already seen the AMC problem. Let's go see some Canadian problems. I just want to make sure I can give you different problems from the North American math competitions, the Canadian problems like the Waterloo series, and also the American problems. And from time to time, I will give you some Chinese problems, some like a Russian problem, just help to expand our horizon. Okay, so this is number, I think it's number 4, right? We're looking at the 2009 Waterloo Katie, problem number 19. Okay, let's have a look. How many integers n are there with the property that the product of the digits of n is 0, where n is between 5,000 to 6,000. How many integers n are there with the property that the product of the digits of n is equal to 0, where n is between 5,000 to 6,000, and this is a close interval. So you can take 5,000, you can take 6,000. Again, $1 million question for you. We're going to do the casework, right? How are we going to do the casework? This is a $1 million question I will ask you forever. How do you get started? Anyone wants to talk something? Yeah, I see Andy has the correct answer right away. You know what? Actually, Matthew's answer is also correct. He knows that we must start with 5, right? Because there's a number just between 5. So the first digit is already taken, right? And then I need to do some magic for the next 3 digits. So this is actually combined with 2 of our technology introduced. The first technology we introduced is that as long as you see this number-related problem or the letter-related problem, normally you do the casework from the first digit, the second digit, the third digit. But in this problem, the first digit must be 5. It's pretty much already fixed by the problem. While the second technology is, I'm going to ask you to do the casework. What is the case? Intuitively, if you read the question, blah, 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 the product of the digits of n is equal to 0. So that means what? There must be some zeros in the digits. There might be 1, might be 2, might be 3. So intuitively, your casework must be follow how many zeros, right? I think this is very understandable. The casework will do 2 things. First, I need to do the first digit is 5, and I'll do the remaining digits. Second is I want to make sure that I want to have 1 0, 1 0, 2 zeros, and 3 zeros. Let's check it out. How are we going to do? Yeah, I see somebody already has the correct answer. Yeah, that's perfect. The correct answer is 272. Okay, 272. So let's check it out. Okay, so we're still in the learning process. Let's try to see how we break them into 3 cases. So case 1, let's say only 1 0. Only 1 0. 1, 2, 3. Only 1 0. So intuitively, the 0 can be here. 5, 1, 2, 3. The 0 can be here. 5, 1, 2, 3. The 0 can be here, right? As long as the 0 is here. So that being said, in these 2 digits, you can do whatever you like. As long as you have no 0, you're good, right? So how many options, how many numbers available for this 10th bit from 1 all the way to 9? How many ones available from this 1st bit also from 1 to 9? So basically you have 9 times 9 equals to 81 different cases. This is quite understandable, I think, right? Same thing. Now, let me change a different color, try to make your life easier. Now we're talking about these 2 digits. The same thing. These 2 digits, each one of them you can take from 1 all the way to 9, And 9 times 9 equals to 81. Last scenario, 0 goes to the 1's bit, and you're talking about the 100's bit and 10's bit. Exactly the same thing, 9 times 9, 81. So in total, you have 243 cases for the first scenario. Okay? 243 cases for the first scenario. Let's go to case number 2. Case number 2 means you have 2 zeros. If you have 2 zeros, when you have 2 zeros, there's not so much flexibility you can do. 5, 1, 2, 3. The 2 zeros can be here, here. 5, 0, 0. Can be here, here. Can be here, here. In each scenario, you can only do some magic for one remaining digit. Basically, 9 scenario, right? 9 for each. Put them together, 27. Easy peasy, right? And case number 3, you have 3 zeros. 0. 3 zeros. 3 zeros, 5, 1, 2, 3. You basically cover the case, right? So there's only one scenario. No more scenarios for the last one. And oh yeah, of course, 6. Yeah, 6. Yeah, because it's actually close. For 5, the question says this n can be reachable at 6,000 and 5,000. So the two endpoints, you can take it. So there are actually 2 scenarios. Another one. So in total, you're adding up your case 1, case 2, case 3 all together. You have 243 plus 27 plus 2 equals to 272. And that is the answer of this problem. So far, so good? Any questions? I think this is fairly straightforward. You just list them out one by one. There's no magic. You just basically list them out one by one. And that's it. All right? If all good, let's go to another problem. Number 5. Determine if there exists positive integer n such that 2018 n cube, 2017 n square, 2016 n plus 2015. That's a huge number, right? Whatever, this guy can be divisible by 3. Can be divisible by 3. Somebody will ask me, is n part of 2019? No, it's 2018 times n cube plus 2017 times n square plus 2016 times n plus 2015. So this is a long expression, right? The question they ask you, please determine, can you find an n to make sure this guy, big expression, can be divisible by 3 or not? I'll give you guys some time, think about it. This is pretty much the question number 5. You already know some technologies, right? So this is not question number 1. Think about it, and maybe somebody can give me some answer. What are we going to do? Well, the $1 million question, again, I want to ask you is, how can I do the casework? Right? This is like a $1 million question for the entire lecture. What is the breaking point of your casework? Yeah, I see somebody has the correct direction. So this problem says you have a weird expression. So the question asks you this expression can be divisible by 3 or by 5, blah, 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 something like that. As long as you see such a problem, okay, this is a very important trick. As long as you see a problem talking about like the modular can be 3, or like it can be divisible by 3, or maybe divisible by 7, the modular is 2, blah, 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 all those kind of things. As long as you're looking at any kind of divisibility related problem, intuitively, your classification must be related for this divisor. One more time. As long as you see any divisibility related problem, okay, divide 3, 5, 6, 7, whatever, your classification must be around this divisor. 99% of the time, your classification must go something like this. N can be divisible by 3. N can be divisible by 3, remainder 1. Divisible by 3, remainder 2. Right? You list out all the scenarios for probably this 3. Like a number divided by 3, either the divisible means the divisor is 0, remainder is 1, remainder is 2. Is that right? If the question asks you divisible by 5, then you just break down 5 different cases. Divisible by 5, divisible by 5, remainder 1, 2, 3, 4. 7, you break into 7 cases. I think this will cover 99% of the problem. Okay, I can't be very absolute, but 99% should be no problem. Okay, if that's the case, let's have a quick look to see how we're going to do this. This is the way how you do the casework. Case number 1, n is divisible by 3. If n is divisible by 3, I'm looking at this. The question asks you what's the remainder if this guy divided by 3, right? If n is divisible by 3, this part will be divisible, divisible, divisible. I just have to figure out what is 2015 divided by 3. What is the remainder, right? That part is fairly straightforward. The remainder will be 2. Right? The question asks you, is it possible this guy can be divisible by 3? So this is not possible. Case number 1, not possible. Let's go to case number 2. N divisible by 3, while the remainder will be 1. 2018 n cube, 2017 a square, 2016 n, 2015 divided by 3. Here I have to use some basic, what we call the property of the remainder. The property of the remainder. Something like this, because we have some students who never been to the number theory lecture. So I'm going to use more human language instead of using the modulo, right? They will get confused. So no problem. Our lectures are specially designed such that different sessions, they're segregated. You don't really have to know some other topics from the other session to understand our topic. So whenever I try to explain the number theory problems, I try to be as brief, as understandable as possible. So, but there's a very important property for the remainder I think you guys can understand. The property goes that the sum of the remainder is actually equal to the remainder's sum. The product of the remainder equals to remainder's product. The difference of the remainder equals to remainder's difference. I'll use some human language to explain this to the guys who are not familiar with this. Something like this. If A divide 3, okay, let me just give you a real example. Sum of the remainder equals to remainder sum. 4 plus 5 divide 3. The remainder is 0, right? Let's check it out here. 4 divide 3. The remainder is what? Is 1, right? 5 divide 3. The remainder is 2. So remainder sum will be 2 plus 1. 2 plus 1 is actually divisible by 3. So the remainder will be 0. Same thing. 4 times 5 divided by 3. 20. 20 remainder 3 is actually 2, right? 20 times divisible by 3, the remainder is 2. It's actually the same thing. 4 divides 2, the remainder is 1, right? And 5 divides 2, the remainder is 2. So 1 times 2 equals to 2, right? 5 minus 4, the remainder will be what? 1, right? 1 divides 3, the remainder will be 1. Same thing. 5 divides 3, remainder is 2. 4 divides 3, remainder is 1. 2 minus 1 to this, right? So far, so good. For the guys, you are familiar with number theory. I'm going to write like this. A plus or minus B modulo M is actually congruent to A modulo M plus or minus or even product B modulo M, right? But if you're not familiar, forget about it. This is not the focus of our current lecture. Okay? So if that's the case, what I'm trying to say is that if N, let me just rewrite it here. 2018, 2017, 2016, 2015, you want to see what is the remainder by 3, then you just have to examine one by one. What is 2008's remainder by 3? What is N's remainder by 3? But I need to do it 3 times, right? So 2008, so let me try to do one. 2008, I think the remainder by 3 is actually 1. 2008 divided 3, the remainder is 1. And N is actually remainder is 1, right? This is our case number 2. Case number 2, N divides 3, remainder 1. So that will be 1 cube. So that's the remainder is actually equal to 1. 2017 remainder is actually 1 as well, right? So that one, you're going to say the remainder is actually 1 as well. That one is already 1. That one is actually 2. So that being said, you add everything together. This guy will be actually 5. The remainder is 5. 5 divided by 3, the remainder is 2. So that being said, this is not going to happen as well. If you are not so familiar with the remainder thing, what I'm talking about, no worries. This is not the focus of our current lecture. Our current lecture focus on what? Focus on the casework. Last part, case number 3 is what? N divided by 3, the remainder is but 2. N divided by 3, the remainder is 2. So 2016 on cube and 3. You really want to check one by one. So this is n cube. So it's going to be 2 cube, which is actually 8. 8 divided by 3, the remainder is actually 2, right? So we want to figure out this and this. You actually figure out this is the remainder only 2. This is the remainder only 1. This is 2. This is 2. Adding them together, the remainder will actually be 1. Okay? The remainder will be 1. If you're not familiar what I'm talking about, it's not a big deal. We're talking about the remainder properties. But for most of the students, I think you've been to the number theory lectures. You should know what I'm talking about. Okay? So that being said, in such a scenario, how many you have? This is remainder equals to 1. This is remainder equals to 2. And scroll up, scroll up. The first scenario is also remainder 2. So that being said, in either case, you n take divisible by 3, divisible by 3 remainder 1, divisible by 3 remainder 2. Nevertheless, you only have either remainder 2 or remainder 2 or, let me scroll up a little bit, remainder 1. So there's no way for you to construct such an expression while the remainder is actually 0. So the answer is impossible. Impossible. So so far so good. Any questions? Oh good. Oh good. Let's go to our last problem. We have already seen some American from AMC10. We see the Katie from Waterloo. So last problem, let's have a look at a AMC12 problem. But again, use the technologies we introduced. Not a big deal. We're looking at a problem at 2018 AMC12B, question number 15. Let's check it out. How many odd positive 3 digits integers are divisible by 3, but do not contain the digit 3. How many odd positive 3-digit integers that are divisible by 3, but they do not contain any digit 3? This is only a one-liner question, but trust me, there's a lot of information for this one-liner, right? They're talking about something what? Odd. Positive is kind of okay. 3-digit integers that are divisible by 3 and has no 3 as a digit. What are we going to do? We just have to list them out, right? using the casework, using the smart classification we talk about from day one. Let's try to have a look how we're going to construct such a digit. Like I said, all the digit related problems, you just try to do your casework digit by digit, digit by digit. So let's say my number can be written as what? ABC, right? This is my number. Okay, A, B, C. Let's have a look. Talking about the first digit, I don't think there's too much constraint. You just want to make sure 3 digits, no digit 3. That's it. Have 1, 2, no 3, 4, 5, 6, 7, 8, 7, 8, 8, 9. Okay? The second digit, let's leave it there for a sec because there might be a lot of flowery things for the second digit. Let's go to our last digit. The question says it should be an odd number. 3 digit cannot be divisible by 3. Cannot have the digit 3. So the last one can be 1, 3, no, 5, 7, 9. Okay, it's quite understandable. Well, it looks like the $1 million question is actually here. How can I decide the value for B? Right? So first of all, B can be 0. B can be 0, right? Can be 1, 2, 3, no, 4, 5, 6, 7, 8, 9. That's pretty much all the options for B digit, right? Looks so check it out. Which kind of condition we didn't use them yet? Which condition I didn't use yet? Who can tell me? I used pretty much all the conditions by the question. There's one condition missing. Yeah, like Andy mentioned, divisible by 3. This is the most nasty, or at least I would try to say, it's not so tangible solution, right? Odd number, no digits are very tangible. But this is divisible by 3, not so tangible. So it looks like I need to do some magic in this B part to make sure this number is divisible by 3. That's the $1 million question. How can I smartly pick up some numbers, right? As long as you have 1, let's say the A confirmed, the C confirmed, right? I want to make sure that how can I do some magic to make sure whenever I pick up the B, the entire number can be divisible by 3. That's it. As long as I do, my work is done. Okay, I see some students already have some ideas. The digit sum is divisible by 3. Okay, that's perfect. And just do a sigma and modulo 3. Okay, that's also perfect. But in your explanation, you are looking at many cases, right? You're going to pick up 1, let's say, give an example. You pick up 2, you pick up 1. Then you'll be able to pick up this. 2 plus 1 is already 3, right? Then you need to pick up 3, 0, 6, 9. Is that right? If I pick up 4 and I don't know, 1, that's 5. 5 is modular 2. Then I try to find a modular 1. Modular 1 will be 1, will be 4, will be 7, right? These are all modular 1. But there are so many cases. It looks like I have so many here, so many here. If I list them out, that's gonna take me forever. This is actually the tricky part for this problem. Like I said, every math competition problem, they're given for some reason. They're not close your eyes, blindly give you a number for the calculator. Sometimes the numbers are so smart designed such that you will be able to pick up them fairly quick. Let's do a quick observation. B can be chosen from 0, 1, 2, 3, 0, 1, 2, 4, 5, 6, 6, 7, 8, 9, right? Okay. Just like somebody mentioned, do a digit sum and divide by 3. At the end of the day, you want to do A plus C plus B, right? You want to modulo 3, or if I use more easy language to understand, I want to divide by 3. I want to check the remainder, right? But trust me, you're going to do this one by one, right? You're going to probably find out A plus C, just like I did. A plus C first. You find the remainder, and then pick up like a B value, which align with the remainder, works smoothly with the remainder to generate a divisible by 3, right? That's basically what we're going to do. But trust me, A plus C. If I want to determine the remainder of A plus C, it's basically 3 cases. Either the remainder is equal to 0, or the remainder is equal to 1, or the remainder equals to 3. That's it. There's no more other scenarios, right? Okay, let's check it out. If A plus C, the remainder is 0, what I need to find for B is a number can be divisible by 3. In our case, is what? 0, 6, 9. Only 3, right? If I pick up a number, A plus C, the remainder, I divide by 3, the remainder is 1. I need to find out a B. The remainder must be 2, right? So therefore, I can plus 1 equals to 0. What are the numbers divisible by 3 that give you remainder by 2? 2, 5, 8. Okay, let's continue. If A plus C, the remainder is 2, I want to find a remainder. So I need to find a remainder that gives you 1, right? 1 plus 2 that equals to 3. 1 will be 1, 4, 7. All right. Can you guys figure out the magic here? It looks like regardless whatever A plus C you find out, regardless what kind of remainder you need, I always have 3 B's available waiting for your selection. Is that right? I always have 3 B's available for your selection. So that being said, I think my work is done. In order to determine these 3 digits, change color, A, B, C, right? Step number 1, I need to determine A's. A is easy. There are 8 values for A. Okay, I'll draw back a little bit. Step number 2, I want to determine C value, right? I want to determine the C value. C value is actually easy. There are only 4 cases for C. Here, there are only 4 cases for C. See? Okay. As long as I have determined A and C, there will be always 3 scenarios for B. Is that right? There will be always 3 scenarios for B. So in total, I'll have 8 times 4 times 3, which give you 96. And that is the answer of this problem. You see? Every single number is giving you such a magic that you do not really have to do the casework one by one for B. If you have this is 4 numbers, oh my God, this is going to be complicated, right? But always they give you the same case. So as long as you have A and C determined, the B will be automatically determined. Always 3. That is the answer of today's problem. All right. I think that wraps up our today's lecture. A quick recap. Today's lecture, we talk about the basic concepts of the counting on probability. We're not even talking about permutation, combination, complicated thing. We just want to get started with some casework. Counting on probability, you need to count first, right? So casework, the most important thing is try to do the smart classification. Make sure there's no overlap, there's no oversight. But the million-dollar question is, how can you make this? We already gave you guys some examples, some routine problem, some number or letter problem. So hopefully you guys understand the beauty of this problem. And during the homework, try to use the same technology, figure out how to do this real things. And I'm going to upload the assignment to the Google Classroom, and everyone, you'll be able to see the problem. You have 1 week to finish the homework. All right. I think that wraps up for today's lecture. Any questions for me? Oh, good. Can I have some feedback? Any questions for me? Oh, good. All right. In that case, thank you for being with me, and hope you guys enjoy the rest of your weekend. And I'll see you guys next time. Bye, guys.